Hello everyone, thanks for attending this session. My name is Ning. I'm working as software engineer for Google Cloud. Our team is mainly responsible for maintaining the hypervisor and the virtual machine monitor inside Google and Google Cloud. Today, the topic of the talk is hypervisor based integrity. As you can probably tell from the name, we are trying to utilize the superpower given by the hypervisor and hardware to provide the guest kernels running inside the cloud environment. So some high-level disclaimer, this is not a statement of direction or planned investment by Google yet. We are exploring this as a possible security mechanisms, and we are seeking feedbacks from the big communities. Some background on why we are heading this way. So Google Cloud offers a product called Shielded VM. In fact, that's the default VM type if you try to create a virtual machine inside Google Cloud. As you can tell from the name, it comes with some enhanced security features. One of them called Secure Boot. On a high level, in case you are not familiar with it, it provides integrity check against firmware, bootloader, and kernel during boot time. It will use the certificates and to verify the signature of all the modules and has been sent correctly, all the drivers and all the binaries it's trying to load. So it gives you a guarantee, like by the end of the boot, everything should be in a very good shape. Nothing has been modified, has been hijacked in any way. After that, most kernel modules, if you try to load additional dynamic kernel modules, it will be protected by the module signings. So that's code in the kernel, which will do signature checkings against the module you are trying to load. That's all good, but in real life, attackers can still find different ways to gain like highest privileges inside a running kernel. If he can do that, and he can modify the code pages or call back in some special way, like all the security gate we put in place cannot be trusted, and we could put user applications in a risk state. The goal is trying to protect the kernel even at runtime. Since we already have all these green box checked during boot, we are trying to extend what we can and help make sure like the kernel at runtime is also protected and can be trusted. If kernel has not been modified in any way and is running as expected, the user application can feel much safe about it. And one more thing is the protection we put in place. It should not be able to turn off from the guest. Because, rootkit can gain highest privilege. If he can change the settings in the guest to turn off the protection, then the protection is not that strong. So let's talk about the threat model here. So we assume the attacker has the following capabilities. So it can gain ring 0 access. It can have arbitrary read and write permissions. So it can read any kernel memory address and write any value to any kernel memory address. So how do we protect the guest kernel based on the threat model we just talked about? First of all, we want to make sure there's no unintended modifications on the kernel code segment and read-only data segment. This is very obvious. We have very well-written code. We don't want it to get replaced by some malicious code. Second of all, we want to make sure the no code execution from other part of the kernel space. Data segment should always be read and write, but not executable. And yes, this is where buffer overflow attack happens, and we want to block that. And third, we want to make sure there's no unintended modifications of key kernel data structures. For example, system call table, which is a table of functional pointers. Hackers manage to replace it with something else. User may get monitored or hacked without realizing it. Another example is control register, like CR0 or CR4. There's a bit in the control register in the CR0 which is write protection. So, but if you turn off the bit, the kernel will the processor will allow you to write to a read-only memory, which is not ideal. And there's other MSR, important MSRs, like there's a paper talking about system enter MSR. And utilizing that MSR, they can hack some system calls. Of course, similar to system call table, there's a IDT interrupt descriptor table and GDT global descriptor table. Both of them has some function pointers. We want to make sure it never get overwritten. Of course, last but not least, we have the page table, which has the mapping from virtual to physical. So if people hack the mappings, they can redirect the code execution to some other place. So why we want to use Hypervisor as another security layer? Our understanding is there's always a risk of protecting guests from within the guest, because we already did a lot of kernel hardening work in the kernel space to make it harder and harder, but it's not guaranteed to be impossible. Rootkit or attacker can still gain like highest privilege and read and write any guest memories if they want. And it's not easy, but it's still possible. So anything we put in kernel space could be risky. But on the other hand, if we guarantee like kernel never changes, kernel code never changes, then basically in return, it will make sure all the security checks we put in place be more robust. So this is not a replacement of all the kernel hardening work we have there. We hope this is just an enhancement layer, like to make sure whatever we put there is correct and remain correct for the entire life cycle of the VM. Hypervisor, on the other hand, Hypervisor has almost one-to-one mappings to all the protection we want to achieve. Like Hypervisor can control read, write, execute bit for page aligned guest memory region, utilizing the two-dimensional pagings like EPT or NPT for AMD. We can set up the permissions which guests can never change. And Hypervisor can protect unsafe modifications of control registers and MSRs. We just configure the VM exit on those write to MSR or control register, and then we can do double check whether that's legitimate or not. And Hypervisor can also protect key kernel page table. There's a new feature called Hypervisor Managed Linear Address Translation from Intel, which allow you to set up page table mappings controlled by Hypervisor, and guests can never change it. And most importantly, for us, for Google Cloud, all of our guests, all of our customer machines are already running in a virtual machine mode. So we already have a layer underneath all those VMs. We are not trying to introduce another layer of complexity here. We are just using the existing layer to make everything more robust and more secure. So how does everything work end to end? Here we want to introduce a new guest security kernel module. This module should be loaded at boot time, ideally by the end of boot time. So the kernel has already set up all the page table, IDT, GDT, system call table, etc. It should be signed and protected by the secure boot, so it can be trusted at boot time. If anyone tries to modify it in some way, a secure boot will fail. And after it gets loaded, it will check whether the hypervisor support special integrity protections. If it does, it will try to identify all the kernel code data segment and address of the key data structures and send a please protect me request to the hypervisor. And then it will need to wait for the acknowledgement from the hypervisor, because we don't want to jump into the runtime so everything become a little bit out of control. During boot time, everything is still in control and in good shape. On the hypervisor side, during boot time, it needs to decode the memory segment information sent from the guest. We'll modify the second level translation table to set correct read, write, execute bit for the specific memory region. And it will configure the VM exit on MSRs and control registers. After that, it should acknowledge the request and let it continue to boot. It's just a few actors we need to call, so it should not have significant impact on guest boot. During runtime, the hypervisor and QEMU or VMM will just handling EPT and NPT access violations. And if that happens, user can configure one of the following actions, can either kill the running VM and dump all the memories for analyze. That's for the people like who care a lot about the security and want to make sure nothing wrong should happen. And for majority of users, we will just log up critical event and notify the user and let them decide what they want to do. Meanwhile, on the other hand, like we do the same thing for the control register and the MSR modifications. And you may be wondering, like, in runtime, we can add dynamic kernel modules. So those kernel modules are executable. So how do we handle that? Our recommendation is much safer to do not do that. But if you have to do that, we have APIs exposed by the guest module. So we'll modify the kernel code a little bit. So first of all, the kernel code will allocate read and writable memory region, then copy binary into it. And once the verification is done, it will call the API to change the code segment of that memory region to be read and executable. So hypervisor will make sure like the code segment never change after the first time you load the kernel module. You may wonder like what's the performance impact since we are doing a lot of stuff here. For memory access, the impact should be minimal. Mainly because we have support through the hardware, Intel EPT or AMD NPT. If there's no violation happens, there should be no impact at all. But if something happens, I think it's okay to pay some extra cost on the VM exit to determine whether the operation is legitimate or not. And from our prototyping and testing, those do not happen very often if it is a healthy kernel. For control register and MSR, the module specific register, the impact should also be minimal. Because we don't expect a lot of modifications on a typical kernel runtime. If you are running a nested virtualization, it's completely another story. So we don't recommend people turn on this if they are running into these scenarios. And for the page table translation, it needs hardware support, but currently only limited to Intel Alder Lake. So it's not there yet. We cannot measure it. It sounds straightforward, but it has a bunch of technical challenges. Two major ones is like how do we distinguish between legitimate kernel modifications? There's a bunch of reasons you can see we list here. Kernel want to modify itself, and we need to work with our customer to either disable those special scenarios in their image, or we need to decode the instruction pointer and go through call stack and whitelist those operations. Another major problem is when set memory permission, not all segments are nicely aligned. If we have one page, because when we set permission, it's on the page level. If we have one page that is shared between a code segment and data segment, it will be very hard for us to set correct permission on it, and we will have a potential problem here. So to mitigate this issue, some change in the kernel need to happen to make sure like all the code segment, all the different segment of kernel is nicely aligned. So here is a quick example of what it looks like if we turn on the protection. We have a guest running on Debian 10. After the kernel boots, we map the entire kernel code segment as read and executable. We got a bunch of EPT violations right away. But if we go through the call stack for each of them, it comes back to the same function, which is text book. The description of this function clearly says it's trying to update instruction on live kernel. So this is a valid case for kernel modifications. After we remove of that particular module, after that, the guest running smoothly without any further violations. This is a very good example to show you, like, if we configure the image correctly, any violations, any access violations will be a strong hint of possible attack. Now let's talk about to support the protection we just mentioned. What are the changes we need for KVM and QEMU? And first of all, we want a common interface to turn on the protection. As you can see, during boot time, the guest agent is sending some message to the hypervisor and the VMM. So currently, we are using select MSR to these configurations. It's not ideal. If we can make allocate a special hypercore just for this purpose, it will show that this is for VM only, and it will avoid a lot of confusions. And once people agree on the interface, API, what a hypercore looks like, any hypervisor or VMM can implement the support for this API to provide the same level of protection no matter where or the VM will be landing. Like Azure, AWS, or Google Cloud, or QEMU, they can all implement the same APIs, so the guests can move freely around different providers and gain the same level of protection. We have a RFC sent out a while ago, so that's for adding a hypercore called KVM hypercore ucore. So this is a hypercore we want to tell the hypervisor to hand over to VMM to handle these special hypercores. We have a link, and you guys can review it. So why we need this change? So today, all the hypercore are handled inside KVM. It never causes any VM exit. But we want hypercore to pass. We want a hypercore interface to pass a control back to the VMM. Why we want VMM to handle this request instead of KVM? Because VMM is responsible for setting up the guest memory mapping and should have knowledge or should control the permission associated with it. And what's more important is it can simplify the support for line migration, because during line migration, VMM could just create the same guest memory region, apply the permission because it has knowledge of everything. And we can keep the KVM simple. KVM just need to expose API we need to turn on the protection, and all the status is maintained in the VMM instead of KVM. So once we have the hypercore defined, we want to define the message sending from the guest to VMM. This is a simple proposal we put here. We want call it HBI request. It's a hypervisor based integrity request. And we have a version and operation code. So for operation, it can be set memory protection, etc., etc. We can extend it for future usage. And for the memory, for the message body, it only need to tell us what's the PFN, page physical number, how many number of pages you want to protect, what's memory permission you want to set on those pages. For the memory permission, it can be read and execute, or read and write. Never allowed execute and write happen at the same time. And once the request is complete, gets able to get the result from this written code. So that's for the protocol, for the guest VMM communication protocol. Other than that, they to correctly set the memory permission, we need to call the KVM set user memory region IPTOR, because unfortunately today the current call only supports setting the memory as read and executable, but we want read and write, not executable. This is something that did not support today. We'll try to extend it. And we also want to expose the ability to do VM exit on control register modifications, because there's a lot of bits we want to protect there. And the hardware Intel, AMD, they support if you config, for example, the VMCS correctly, we can get the exit on control register 0 or control register 4. And we want VMM to make a call whether we let the modification to go through or we should not. And last, this is basically support the new Intel Hypervisor managed linear address translation. Since it's new hardware, I don't think what is there. I hope Intel or some community members or us will work on the support for this together. And for the future, once we have the protection we talk about in place, we can extend this guest security module to expose APIs for any kernel code to consume. It can be a driver, it can be a security hardening code inside the kernel. So they can call the API during boot, allocate a memory, and write to it, and then mark it as read-only. So we will send this memory segment to the hypervisor at the end of boot, and then we make sure those memory will never change during the entire lifetime of the VM. So yeah, all the kernel security and driver modules can take advantage of this to protect themselves. Now let's talk about some other security considerations. So first of all the protection we talk about today is built on top of secure boot. If secure boot is broken, our guest agent could be changed and we cannot trust the message sent to us. So why can we trust secure boot in Google Cloud? For Google Cloud, all the guest firmware, like the UV firmware, is actually immutable. We inject the guest firmware during boot time, we copy it into the guest memory. So even if you manage to change the firmware in some special way during runtime, after you reboot, you will get a fresh piece of firmware and it will restore back to the good state. A lot of firmware integrity check is actually happening outside the guest. We know that's a critical piece of code. We want to make sure it's doing what we expect. So a lot of security check, signature check is happening. We upload all those logic into the VMM processor. It's not happening inside the guest. And for important security boot variables, primary keys, signatures, they are stored on a remote server instead of your local disk. So there's no way a guest can skip UV, can skip our firmware to modify those variables directly. One popular attack against secure boot is through system management mode, called SMM attack. To reduce the attack surface, the SMM is completely dropped from Google Cloud. We don't support it at all. But the protection is not perfect. Even if we guarantee the kernel code stays the same through the entire runtime and nothing gets executed outside this kernel code space, there's still possibilities people can use something called return-oriented programming ROP attack. What it does is trying to find some instructions on your executable region and chain them together to achieve some special goals. For example, if people use ROP attack to modify the kernel page table, it will still break the protection because you can modify the page table translation and point the kernel code to a different memory location. And if that happens, that memory location is no longer protected by any EPT or NTP, so the hacker can do whatever they want there. To mitigate this problem, I think kernel stress randomization is very popular today. To make ROP attack a little bit harder, and there's ongoing work for the kernel control flow integrity to make sure make it harder to happen or make sure it never happen. And there's hardware support like the hypervisor managed linear address-based translation we talked about earlier, where you can make sure the address-based translation is happening on the hypervisor side, so that can avoid people hack this page table in some special way. To summarize this presentation, we are trying to propose a hypervisor-based reinforced protection for guest memories and system registers. And we want to also provide a parallel virtualization interface to enable this protection. And we want to enable security by default. This hardening we are proposing here is to extend the secure boot and provide runtime protection for kernel integrity. Thanks. That's it.